Good afternoon, everyone. My name is Qifan Zhang. I'm now a fifth-year PhD student from University of California, advised by Professor Zhou. Today, I'm very honored to present my work, ResolverFuzz, automatic discovery of the DNS resolver vulnerabilities with query response fuzzing. So let's first talk about the object we're gonna fuzz. It is domain name system, which is DNS. So what is DNS? You can imagine it is kind of like a translation between the human-friendly internet domains into the machine-friendly IP addresses. For example, if you want to know the IP address of USENIX.edu and you got the answer of this IP address, so DNS is gonna do the magic to translate the USENIX.edu into this IP address. So in detail, for DNS infrastructure, for example, you are a client, and which is also the sub-resolver, and you want to know the answer of the full.com, you're gonna query the recursive resolver, and the recursive resolver will first gonna query the root nameserver, which is the root NS, for the TLD nameserver. In this example, it is .com nameserver, and after that, the recursive resolver gonna query the .com nameserver, and after that, it got the SLD nameserver from the TLD server, and finally from the full.com, you got the answer of the full.com IP address. And finally, it is 8.b.c in this example. And we know that DNS is very important, but unfortunately, DNS failures and attacks happen a lot. And the most severe one in recent years is Facebook outage, which happens in 2021. And this outage leads to a very severe outage of the Facebook apps like the Instagram and Facebook. So unfortunately, we found like for DNS, it is very fragmented and sometimes even problematic, and you can find the timeouts, bad certificates, and whatsoever those problems. And is there any existing work analyze the DNS? And of course it is yes. So the first part of these previous works is the attacks, which for example, the SAT-DNS published in CCS 21 and 2020, and the cache per ref attack, which is a little bit longer years ago. But they are all manual analyzed, and we lack of automated large-scale vulnerability analysis. And we also have those automatic vulnerability analysis ways, for example, like the formal analysis by the fuzzing. But for those previous works, they either focus mostly on the authority nameserver, but not those complicated like recursive resolvers, or they lacked analysis on the real-world DNS resolver implementations, especially for the formal analysis, or they are not specially tailored to the DNS resolvers. For example, the SnapFuzz published in ISSTA 2022. And after that, we found like there is a very unfortunate fact that no one has ever done the effective automated analysis on DNS resolvers before. So we plan to take this challenge. So with regard to find like those bugs in automatically, we're gonna do fuzzing, which the full name is automatic fuzz testing. And till now, the most advanced and frequent used technique for fuzzing is coverage-based gray box fuzzing. And the most frequently used and the most famous tool is the macro fuzzing loop, which is AFL. So for the coverage-based gray box fuzzing, we got input set, which we call them like seed corpus, and run the program we want to test. And during the goal of this testing is to find the crash in the program. And during the execution, the program is orchestrated with tools so that we can collect the information, especially the branches within the program, and got those feedbacks to the inputs to better optimize those inputs in the next few rounds. And finally, with those information and the inputs, we got the vulnerabilities within the program. Now we have this kind of conventional fuzzing tool. So what is the challenge to fuzz DNS? We conclude 3 challenges for this one. So the first one is non-crash bugs. So for DNS, most bugs, or we say like a lot of bugs for DNS, is not crash. For example, the cache poisoning, the denial of service, and the access violation. They are not always crash. So how could we find those bugs, and how could we like decide which bugs should we focus? So we decide to learn from the past. And we learn from the past and find those bugs which is more frequently spotted in the previous works. So that's why we do the DNS CVE study. We studied those CVEs during the past decades, and we found especially that 109 out of those 245 CVEs are non-crash CVEs, which is a significant number. And also we found there are 93 crashes, which is non-memory crash, for example, association failures. And this CVE comprehensive study guide us how to design the ResolverFuzz. And the second challenge is about stateful fuzzing. So let's recall the conventional fuzzing. It is stateless. So what is stateless? Stateless is like we have one input and we have the program. For each round of testing, we test the program with those input, and then it's done. The seed is not used anymore. But for DNS, it is stateful. For example, like for a DNS, we have cache. If you are querying a DNS server, a resolver with empty cache, or with the DNS server with cache entries, the response time and even the responses might be different. And also for DNS, it has multiple parties. Like they have the client to send the query, they have resolvers, and also nameservers which hold the referral records. And let's see whether this kind of stateful DNS resolver could be used, could be fuzzed by the stateless fuzzing. And the answer is unfortunately no. For example, if we only have the query without response, and this CVE cannot be reproduced. And on the other side, if we only have the query but without response, and this CVE gonna not be reproduced. And also, if even we have query and response, but they are not like properly collaborating with each other, the efficiency is still quite low. And the third challenge is a multilingual system. For DNS, for DNS implementations, most of them are implemented in C, C++, C#, Go, and even Rust. And they are working on multiple operating systems. So if you want to simply use the AFL, it's gonna not be working for all of them. With those challenges, so how should we design ResolverFuzz? We decide to design ResolverFuzz into a black box stateful and grammar-based fuzzing with 2 input generators. And after we collect those outputs, we will identify those different vulnerabilities by different oracles. And here is the workflow of ResolverFuzz. To address challenge 1, we have the client and the nameserver as the 2 inputs for to test the resolvers. And for each round, we have a test case generator, which generate those cases in pair, the query and the response in pairs with a preset grammar. To address challenge 2, we have the nameserver, and we preset a duration of time for the resolver and the nameserver to be communicate with each other, so the resolver could be tested comprehensively. For the third part, we collect all the data during the testing, including the cache response, the system log, and also the traffic. And finally, with those data collected, we're gonna do the differential testing and find the discrepancies and finally the vulnerabilities within those resolvers. In detail, we have those techniques in ResolverFuzz. For example, we write the grammar in a variation of the context-free grammar, CFG, which is probabilistic context-free grammar, PCFG, with probabilities assigned for the terminals. And we also adapt the bi-level mutations for a certain proportion of those test cases. And we have query response fuzzing inputs, which means like we have a pair of query and responses during one test. And also we use differential analysis, differential testing for the vulnerability analysis. For example, we use a bisecting k-means for cache and poisoning analysis. And after that, we evaluate ResolverFuzz. So we in total test ResolverFuzz in 4 popular modes. It shows a good coverage of different field and values. It is efficient in runtime. And also we found 23 vulnerabilities with 19 confirmed, 15 CVEs assigned, and categorized in 3 classes. This is the 4 modes we test. It is like resolver only mode and the forwarder only mode, and a mixture of those 2 modes. We also test, we will also do the analysis on the test case generation. So we have different probabilities, or we say different weights for each terminal, so that we can test certain code logic more intensively. And it shows as shown in the figure, it has a good coverage of those fields. And these test cases are prone to trigger errors. We find that only 17.8% of those R code is non-error, which means it is very easily to trigger those exceptions during the resolvers. And also, our runtime performance is very good. And we use concurrency to speed up. We have we show a 5.9 query per second QPS for CDNS with fallback mode. And for other parts, we have 2.8 QPS, since some of the DNS software is low in efficiency. And finally, we find like this matches with a real-world DNS resolution, for example, like the Google DNS. And finally, we find like 23 bugs, and 15 of them assigned with CVEs. And it obviously outperformed the two GitHub repos, which is DNS Fuzz server and the DNS Fuzzer and the stateful paper. And this is a conclusion table, the concluded table for the vulnerabilities we found with ResolverFuzz. And in particular, we have 3 other top-tier conference papers published to analyze the vulnerabilities with the detailed analysis in other venues, which is Maginot DNS, Phoenix Domain, and Tudor attack. And in conclusion, we first conduct a comprehensive study on DNS CVEs. And then we propose ResolverFuzz, a fuzzing system tailored to DNS resolvers with a technique of constrained stateful fuzzing, differential testing, and grammar-based fuzzing. And we in total identified 23 vulnerabilities with 19 confirmed, 15 CVEs assigned. And it is mentioned to say that we have 3 top-tier conferences published with detailed analysis on the 3 discovered vulnerabilities. And of course, our work has limitations. For example, we only test a subset of DNS, which is like, for example, tens of DNS records and without DNSSEC. It is not fully automated, and the vulnerabilities needs manual efforts to do the analysis. And we only have a fixed timeouts, the test duration, and we only have 1 pair of query and response, so it lacks the long sequence testing during 1 test case. And for the CV study, it might suffer from survivorship bias, since like easier and shallow logic of vulnerabilities may be easier to be discovered. And that's all about my presentation. And thank all the authors and audience for your attendance. And especially I want to thank Xuesong Bai, my lab mate, and my advisor, Professor Zhou for their irreplaceable efforts and ideas and their inputs during the whole process. And thank you everyone for your listening. And I'm now ready for questions.